Welcome all to this 10th session of Statistical Learning in Practice. Today is going to be a theory session, and we're going to continue with generalized linear mixed effect models, and then we'll introduce quasi-likelihood, and with this we'll quasi-likelihood methods, and with this we'll close basically the regression block of the course, and then we'll go into classification in the next theory session. Right, so as I'm saying, let's continue then with this generalized linear mixed effect models. And so firstly, let's introduce the data that we're going to be using, or the format of the data that we're going to be using, because it changes slightly with respect to, or compared to generalized linear models. So let's say data, then rather than having, so we're going to have the usual pair of data X and Y, although indexed in a slightly different way, right? Because now we have two indices rather than one. And we also have a third component in the data that we're going to denote by Z. And so I will tell you in a sec what that is, but it's basically covariates as well. And the I index is going to go from 1 to capital I, and this denotes, represents the number of groups that we're going to have dependencies within, and not between them. And then the J is the number of subjects, or the number of observations within each of the groups. Yeah. So, so we have here a capital J that may depend on the I index that we have, yeah? And we have essentially that, or the condition, and such that, if we denote by N, so this is the sample size, right? The sum of, of all of the, sorry, not N, but rather the capital I, the sum of the J's, okay? So that's going to be the small n, of course. Then we get that, we assume that this matrix, which is, comprising all of these guys, so up to iji, transpose, well, it doesn't really, okay, yes, but the definition, then that's what we need. And this belongs, of course, to Rn times P. And also, let's define the capital Z as, again, just the same story. So we have this here, and this belongs now, rather than to N times P, we're going to write Q, okay? So the assumption essentially is that these two matrices, they have ranks P and Q respectively, which is, and both of them have to be less or equal to N, okay? So this is the usual assumption. So now let's define these models. So a generalized linear mixed effect model assumes the following. So it assumes that the Yij, given some Ui that I will specify in a sec, so they follow a distribution that is an EDF. Okay, so this EDF, as usual, we have a mean and a dispersion parameter, and this is for I. Let me just be a bit, just write it here, just because I've already defined these guys. I shouldn't, yeah, so that's clear, I think. And what are the assumptions? Well, the assumptions are that, so where G, so the usual thing of the GLM, so we have this link function that is going to link, the mean to the linear predictor. And what is the predictor now? Well, It's this guy, but we want to use now also the other covariates that we have. So this is Zij transpose, and here we multiply precisely by this vector of ui. So G is, as usual, this is known. Beta in our P is unknown. And this is what is called the fixed or the fixed effects. So fixed effects, yeah. And then what we have for the U, for the UIs, is that these guys follow a certain distribution, capital P, with, so these are what are called the random effects. Okay, and so this is for some distribution P and unknown parameter alpha, which is going to belong to R. So R, let's say, yeah. Okay. So this is, by the way, so this way of introducing these models is what is called hierarchical formulation. Okay. Okay, so we'll see that there is another formulation that is called the marginal formulation, and this we will see as we go along. Yeah. Okay, so remarks. Okay, so first remark is that, so this is a bit what I was saying last time. So we're going to model, so we model the dependencies within a group, and we do so via modeling the means. Okay, so by modeling the means as realizations of this random variable, right? Okay, and what this means is that, you know, we can account for these longitudinal studies, right? Because I mean, we will see examples of this, especially in the practical, we'll see the example, a good example. So basically when you have, for instance, well, I mean, I spoke about this. So there's just measurements from, you know, the same person at different times, at different times. And so, of course, you know, you could, for instance, by the way, be introducing a different, you know, parameter for each person. And then in that case, you could then have a GLM in which you have a factor that basically is, you know, the subject, and you could be estimating, you know, that, but in many occasions, you know, that will mean that you have a bit too many parameters, and in many occasions you also don't care about the differences between subjects. And so when you don't care about this, then you can introduce a random variable and then it just takes values, and you don't really worry about you know, trying to have a GLM in which you understand the value of each of the coefficients for each person. Okay, so so yeah, so we have these longitudinal studies, but also we can model other things with this, right? We also have like missing covariates as an option to model, right? Because we are, at the end of the day, we are modeling this image of the mean through G. So, you know, it could be that we're missing covariates there. And so then that's exactly at the right level to account for these. And we could also be modeling measurement errors in the covariates. Okay. In these, yeah, in the covariates. Okay. All right. So second remark is that generally what we have is something slightly simpler than what I introduced. So generally, all over ji's are going to be j. Okay, so this is going to be some value in natural numbers, and the other thing is that the ui's are independent. Okay, so these two things are usually assumed, and then on top of that, sometimes we assume normality. In fact, in the practicals, we'll see that this is inbuilt in some functions. Okay, so this is for sigma being q times q, non-degenerate, of course. Non-degenerate and positive definites, right? So examples of this are, so for instance, we have the normal linear mixed model that we'll see in a second, but we also have what are called, logistic normal, and also the Poisson normal. Yeah? Models. Yeah? So we'll see this in the practical. Okay. So another remark is that a particular case that is important as well. So particular case is when the zij equals 1. Okay, so this is one dimensional then, and this is what is called a random intercept model. Okay. Okay, so in the example sheet, the one that you've probably looked at already, we have that in the negative binomial model is actually of this kind. Yeah, so you may have realized this now. Yeah, by now. The negative binomial model. Okay. So what we say is that it mixes the Poisson distribution with log gamma distribution. Yeah. And this is expressed. So of course we haven't expressed that model in this hierarchical formulation, but instead what we've used is what is called the marginal formulation. Okay. Via the marginal formulation. Okay, so I think now it should be clear that what we mean by this formulation is that we give the distribution of the responses not conditional on the random effects. Yeah. Okay. So now fourth, so let's talk about estimation, or it doesn't need to be a remark. I guess I could just talk about estimation and so on. Yeah, okay, maybe that's a better idea. So let's say, so how do we do estimation? So we can estimate, the two parameters now that we have alpha and beta. So we can estimate these via MLE. Now, however, this is not simple actually. And let me show you why. So if yi is, so let me denote by yi precisely the set of responses that correspond to the ith group. Okay. Then the log likelihood for this, well, not the log likelihood, excuse me, the likelihood for this guy. So of course, if you wanted to look at all the y, then it would be the product of all of these because they're independent. Well, at least assuming independence of the ui's. Then what is this equal to? Well, this is just the integral of this density, so density of the yi, given the the random effects and the parameter, and then we integrate with respect to this guy. Yeah, maybe actually let me just say that we don't need the I really if we're integrating. So this is alpha, and this is with respect to u. Yeah. So we are assuming that there's a density with respect to Lebesgue, but it's not. You see, you know how to adapt this to the discrete case if needed. Okay. So of course, what we see is that in general there is no closed form. Yeah, there's no closed. Okay. So what does one do? Well, you need to approximate this integral, numerical methods, and optimize then also using numerical methods, right? Okay, so it's not the simplest methodology. Okay, now for prediction, so you imagine that you've been able to estimate alpha and beta. Well, the problem is that you're gonna need the UIs, right, to make predictions. So how do we get around that? So let's see. So for prediction, so for prediction, we need the values of the random effects. Yeah. And these, of course, are unobserved. Okay. So what do we do? Well, we can use Bayes' theorem as follows. Yeah. So let's look at the guy that we're interested in, right? So it's this conditional density. Well, you can check that this should be proportional to these other guys, or the product of these other guys, which is, the guy that we can access, is given in the hierarchical formulation, and then times the marginal for the use. Yeah. Okay, that's great, because then we can, what we can do is to substitute alpha and beta by alpha hat, beta hat, so our estimators, and maximize. Yeah? The right-hand side, of course. Yeah. Okay. This will give us what we'll denote as U tilde, okay, or the UI tilde, and it's called the map estimate. Okay, so map for maximum a posteriori estimate, yeah, or estimator. Let's say estimator. Okay. Okay. So then, what about testing? So testing. Let's say so. Testing if we have nested GLMMs, then we use the usual, use the likelihood ratio test statistic and Wilks theorem. Yeah. Okay, so that's the usual thing. Now, the problem is when we wish to compare a GLM with a GLMM, right? And okay, so then maybe interested. Okay, so sometimes interested in H0 being, this a GLM, so let me be a bit vague here, versus H1 being a GLMM. Okay, and of course, H0 is at the boundary of parameter space. Of H1. Yeah. Okay, so in this case, because it could be that we have several parameters that, whose, for instance, whose variances we're setting to 0, then we're going to introduce, and I think I anticipated this in the last practical. So we introduce, or maybe it was in maybe it was in an office hour. So we introduce parametric bootstrap. Okay. Although so this is also, by the way, a way to get around the fact that the type of results that we're using are asymptotic. And so, of course, these are, approximations that may be very rough approximations when we have small sample sizes. And then the other issue that we can avoid by using parametric bootstrap is that in some occasions, these limits that I'm talking about of these asymptotic results depend on unknown quantities, right? And these we need to estimate. And so you have a succession of approximations that, of course, may mean that they're not very good approximations. Excuse me. Okay. Yeah. All right. So before I say that, let me remark that. So although there is one case in which we can have in which we know explicitly the limit of some asymptotics. So although note the following, which is that if the GLMM is a random intercept model, okay, then, which is, of course, to say that this guy's, well, it's not to say this, but I guess I mean, by that, so maybe we should say a random normal intercept model. Okay, so normal. Okay, then we have this here with this guy being greater than 0, and so the likelihood ratio test statistic converges to precisely this mixture of a Dirac delta at 0 and a chi-squared 1 degree of freedom. Okay, so it goes to infinity, and this is something we've seen already in the negative binomial model, right? So that's an example of this. Yeah. Okay, so let's introduce parametric bootstrap then. What we have, so we have parametric bootstrap. Okay, Right, so what's the setting? So the setting is that, so we let y have a certain distribution, p theta naught, where p theta naught, of course, belongs to some space of distributions. So we're going to write this as that, where the theta, belongs to the parameter space capital theta. So this is just the same setting as usual, but just a fixed notation, and the theta naught is unknown. So let now psi be, a functional that is going to depend on the theta. So this is a measurable functional of interest. Okay, so examples of these are, the identity, for instance. So as in we're interested in the theta itself, or we're interested in the deviance, in these GLMs. Okay, and then the next thing is to write this psi hat, okay, which is just the image of the estimator that we have at hand. So this is what we call the plugin, estimator of this psi. Okay, and this psi, of course, has to be the one that depends on the true parameter. This is the one we're interested in for some, and this is for some estimator. So it doesn't need to be the MLE. So estimate theta hat of this theta naught, and it must be computed from y. Okay. Now note the following. So this estimator, of course, is a function of the data. It's a measurable, in fact, function of the data. That's the definition of any estimator. And so what this means is that the distribution of this psi hat is determined by the distribution, by that of y, of course, right? So, the latter is unknown due to not knowing the theta naught, but can be estimated, right? So by p theta hat, right? And so once we can estimate that, it means that we can estimate the distribution of this guy. Okay, so how do we do that? So first, let's sample some new sets of data, independent sets of data, and these are going to follow precisely this distribution, right? And this is for B1 to some capital B, of course, in the natural numbers, and we compute the estimator for each of them, okay? And also let's compute this psi now hat that is going to depend on the set of data, and which is simply given by the image of the estimator. Okay. So now that we have that, well, so we do these, of course, for B from 1 to capital B. So we have a set of values for this psi hat, and therefore, the law of this psi hat can be approximated. So approximate the law of this guy by this empirical distribution. Okay, the following empirical distribution. Over capital B, the sum from B equal 1 to capital B of delta psi hat B. Okay, that should be clear that this is an approximation, well, a reasonable approximation. Anything is an approximation, but this is a reasonable one. And then what it means that, well, or the implications are that we can build inferential procedures now, yeah? For this psi naught, okay? And let me give you an example. So assume, without loss of generality, that in this functional that is taking values in the in the real line, then we have that these guys are ordered, okay, increasingly. Okay, so that's, we use no generality in assuming that. And also let's take B to be 100. That's fine. So then what we have is that if we take, the set of real numbers between the 2nd and the 97th, then this is an asymptotic 95% confidence interval, right? For this psi naught. Yeah. Okay. Okay. So then let's now talk about the linear mixed effect models. So we'll see a second example for testing, by the way, using parametric bootstrap, but we'll see this in the practical, and just simply because it's a bit involved. So I will write it in the notes, but because it is a bit involved, I think it's much better to just see it in the practical directly. Okay. So to see it in practice, basically. So linear mixed effect models. So this is a particular case, of course, of the previous models. Okay, so we shorten this by LMEM. Okay, so now you may realize that, of course, in the linear, in the linear model, there is no over-dispersion or anti-dispersion. So you could be wondering, well, why on earth then do we do this? Well, I mean, we're introducing models that deal with over-dispersion, but it's not the case that they are only useful for that, right? So in this case, what we have is that these linear mixed effect models are going to be useful for or relevant in modeling dependent data, right? Okay, so definition. So definition 9. Okay, so definition 9 says that the linear mixed effect model assumes that the responses are given by this expression, okay, where we have several, I guess, assumptions. So first, we have that beta in RP is unknown. Sorry to be writing this again and again, but this is, the fixed effects. Then we also have the Z tilde. Okay, so this is a block diagonal matrix. So it's block diagonal with the ith block given by precisely the Z's. It's a bit different from the capital Z function, matrix that we had before, in that it contains these blocks in the diagonal. And so let's see, another assumption is that the U's, so we're going to write them in this sort of continued, or in this, yeah. Okay, so just in this way, yeah. So one after the other, and we're going to assume, of course, that, so as you expect, that these guys are independent and normally distributed. Okay, for some, of course, this guy is unknown, yeah? Non-degenerate. Okay, and then last, just the usual assumption that our, errors are going to be normally distributed and independent, yeah, between them. And we need, and this is important, we need independence between the U's and the epsilons. Okay. All right. So we could introduce these linear mixed effect models in a different way. So alternatives. So alternative, I guess, definition. Okay. So this is via, for instance, the hierarchical formulation. Let's move a bit like that. So formulation. What's this? Well, we could assume that the y is given by, when we condition it on the U's, is given by a normal distribution with mean x times beta plus z tilde u, and this is distributed now with this variance, right? So that's sigma squared with the u, as above. So okay, so just for clarity, let's write it out. So it's this with the ui, being independent realizations of a normal distribution with this capital sigma as above, yeah? Or, so I'm just basically rewriting these things so that it's very clear what the hierarchical and what the marginal formulations are. So marginal formulation is then, so we need to work out the distribution of the responses. And so this is simple in this case, because this is given by a normal distribution with this mean and variance capital V, that is going to be, a function of the sigma squared and the capital sigma given by Z tilde and then sigma tilde Z tilde transpose plus sigma squared IN, where this guy is a block diagonal matrix with every block being equal to sigma. Okay, I think that should be clear. Okay, so then now from the marginal distribution, formulation, we can deduce something, which is the following. So, so from y being distributed as this, we deduce that the log likelihood for these guys is given by, constant minus 1/2 of the log of the determinant of the v. Okay, so this is just the standard things, minus y minus x beta transpose, and then v rather than sigma, sorry. So v y minus x beta. Okay. And what can we say from this? Well, we can say that the beta hat, which is the maximizer, arg max, over RP of this L, okay? So this is going to be, by the way, a function of the V is given by, this is just, you know, by the usual calculations, is given by this in here, okay? So I think actually, so I'm missing -1. I'm missing -1 here. Okay. All right. So then, you know, this way we can work out the MLEs. Okay. So MLEs, or the MLE even of sigma squared follows. Yeah. So how does one do it? Well, I mean, it's very simple, right? So you plug in this beta hat into the log likelihood, and then maximize with respect to you know, with respect to sigma squared and the capital sigma, and then okay, and then we can, so then, and then MLE for beta is precisely beta hat with you know, this hat V. Okay, so V hat, of course, being, I'm just being a bit picky here. Okay, so it's that. Yeah. All right. So now the problem with that, and we need to, so I need to make a remark here, is that the MLEs actually are not so great in this case. So the MLE or the MLEs, or MLE for sigma squared capital sigma has drawbacks. Okay. And this is bias. Okay, so they are biased as in the normal linear model, right? So remember, in the normal linear model, with the, so if you estimate the sigma squared, then what you get is that it has a, so so it's multiplied by 1 over n, right? So it has this normalization, but that's not the right one if you want it to be unbiased. So you need to divide by n minus p rather than n, and you know, in this sort of effect also appears in these estimators. And then the other thing that is also that is probably worse is that the so let me just say it in words. So is that we require, of course, that the capital sigma is non-negative. Sorry, is positive definite, and what this means is that what the problem that can happen is that when you're maximizing the log likelihood, it is maximized by something that is not positive definite, and so in that case you're going to have instabilities in the optimization, and it is going to be quite hard actually to restrict yourself to these positive definite parameters. Okay, so what is the alternative? Well, so the alternative to MLE alternative is something that is called restricted. So restricted maximum likelihood approach. Okay. And this is written as Gremlin. Okay. Okay, so what's the idea behind this approach that we're going to be using together with the MLE in the practical? The idea is that, you know, this beta, so the idea is really just to try to estimate it, or to estimate the, you know, this variance parameters directly, okay, rather than going through the beta estimator first. Okay, so how does one do that? Well, okay, so the idea basically is to consider estimating the V directly so from linear combinations, okay, of the okay, let me just write it and then I will comment on it. Linear combinations A, K, transpose Y of the observations, okay? Okay, and such that AK transpose times X equals 0, right? And that should be clear why we're doing this, because if we if we have such linear combinations, then of course the beta bit is going to get killed, and we're going to be able to estimate the variances directly. So how do we do this a bit more in more detail? So let A1 up to AN minus P, right, be an orthonormal basis of the orthogonal complement of the column space of X. Okay. Then let's say write A equal to these guys. Okay, so then what we can do is what I just said in words, which is that we can take this set of values, and this is going to be, of course, distributed according to normal distribution with 0 mean, right? Because now we killed the mean, and in the variance, we're going to have this here, right? And so we can estimate this by maximum likelihood estimation, okay? Oh, well, okay, so let's say let me say it explicitly. So by maximizing the likelihood of, well, arising from this W, okay? By the way, of course, this will change the values of the beta, right? Because we estimate this, and then we plug it into the beta expression that we had above, the beta hat here expression that we had, and so it will change the estimator as well for beta. Okay, right. So let's now end the blog with these quasi-likelihood methods. So 1, 2, 4 quasi-likelihood methods. Okay. All right. So okay. So what are these methods about? Because we're saying quasi-likelihood, so that's a hint in itself. And so what we have here is that, in some occasions we may not think that the distribution we proposed is a good approximation to the, to the empirical distribution that we observe in the data, or, or simply we just want to be a bit agnostic because we're not very sure about what the distribution of the right one should be, or, as we saw with over-dispersion and under-dispersion, it may be that, the distributional assumption that we're making implies some limitations, right? So then why not simply, sort of get rid of any distributional assumptions and just impose moment conditions, which is what we were interested in the whole sort of in this whole block. We were interested in modeling the mean, and then the variance sort of followed, and we had a certain relationship between the mean and the variance that sometimes as well can be limiting. Yeah, but anyway, so what about just assuming those things? So that's the idea of quasi-likelihood. So again, we don't make distributional assumptions, maybe not beyond the first two moments. Okay, so definition 10. Okay, so y1, yn follow a quasi-likelihood model if we assume that, just as I was saying, that the mean is given by this g minus 1 of the linear predictors, and the variance yi is given by some function of the means, okay, which can change with the data point that we're considering. Okay, let me write here star because we'll be referring to it. Okay, so this is for some, so as usual, for some functions g, nu1, and nu n known, okay, and with the usual conditions that we have, I mean, for g, generally speaking, okay. Okay, so what we see, of course, is that this is a generalization of GLMs, right? Yeah, this is a generalization of GLMs that is going to allow for over-dispersion directly, right? So this is, maybe let me remark here. Remark, quasi-likelihood is a generalization of, well, or generalizes GLMs, okay, in that we're not assuming any distribution, and allowing for over dispersion and under dispersion. Okay, so for instance, let's look at Poisson-like. We have Poisson-like counting data, then we assume, well, or take, actually, rather than assuming, let G be the logarithm, and the new i's, we can take them to be phi mu I. Okay, so we're simply sort of generalizing this bit as we wish. Yeah. Okay. Okay. So far we've only said, that we have these two assumptions, but then, generally speaking, we would use maximum likelihood estimation. But if we don't have a distributional assumption, then we don't have likelihood. Okay. So so how do we estimate the parameters then? So well, what in these quasi-likelihood methods do is to assume that we have something that is similar to the score function. Okay, well, similar, it's just the same thing. But of course, it cannot be a score function because it's not, it doesn't correspond to the derivative of any likelihood. But we can still sort of proceed as usual. So we estimate beta via the score, the quasi-score function. And this is this Q. Okay, I'm going to define this Q excuse me, not Q. Why am I saying that? It's U beta Y given by the sum of, so this is exactly the same that we would get in a GLM. Okay. Okay. So quasi likelihood estimator is beta, and now we're going to invert the hat. So this is a tech. So this is one of the maximizers. Okay. Of this bit. Right. So let's make then a few remarks, and then we're done with this. So remark. First remark is that if star, so remember that we wrote star here. So if the two assumptions hold, so if this holds, and then of course we need other assumptions, but I will ignore this. Then it turns out that this estimator, this estimator is asymptotically efficient. So that just means you have the minimum variance that there can be, and this is among linear estimators. But anyway, I mean, it's fine. We don't need to be totally precise because that's in the other assumptions basically. So with covariance given by the same quantity that we had before. So let me just write, okay. So capital sigma as the limit as n goes to infinity of n times x transpose w x minus 1, and with w equal to the diagonal matrix given by with these values here. Okay. So this should be very familiar to everyone, yeah, because we're recovering basically the GLM large sample asymptotics. Okay, so that's great news. Okay, second, in particular, if we have, just as in the example before that I showed with Poisson-like data, so if we have the new I mu is phi times some v, capital V, okay, which may depend on the, well, no, let me not make it depend on the I, at least not for this remark, and you don't need to. So if this is this, with V coming from a GLM with dispersion 1, okay, then what we get is that the variance of this guy is going to be approximately the variance of the MLE, but multiplied by the phi, okay, by the phi estimate. Well, not the estimate, sorry, by the actual phi. Yeah, and you can check this by essentially, in the new I's, writing this phi that comes out and checking how it pops out in the W, and therefore in the limit capital sigma. Okay. All right. Then the third remark is that, so we'll use this second remark in the practical. Yeah. So that is actually quite a useful remark. So the third thing is that if the new I's, equal phi v, and now we can make it depend on this. It doesn't need to be from GLM necessarily. But if we have this, then we can estimate this dispersion-like parameter by exactly the same generalized Pearson statistic that we had before. Okay. Now, depending on that beta check, okay. And of course, the usual things. Okay. Okay, and 4, if only the mean, well, the first, well, the mean, because it's equality in star holds, we no longer have this asymptotics that we were showing, but we still have that the beta check will converge to beta. Okay, so we have consistency. That's what I mean. Yeah. Okay. Sorry, and let me just say one more thing, and is that, and this is just a comment, so we can also modify the quasi-likelihood, the quasi-score function to account for dependencies. Rather than I mean, it can be modified. Yeah, this is out of scope of the course, but it's just to say that we can account for dependencies as well, even without even without distributional assumptions. Yeah. Okay. Or without full distributional assumptions. Okay. Good. So I will see you in the practical, where we're going to see these methods in action. Right. Thank you for the attention. Bye now.